Hello, today we are going to be talking about optimization. Optimization is one of the most common ways that calculus is utilized, and you'll hear it a lot. You hear it when you hear things like least time, greatest profit, shortest distance, maximum volume, minimum waste, things like that. All of those are calling for optimization. So when we're doing optimization, we need to be able to have a quantity that is minimized or maximized, and we need to be able to assign variables and kind of write a function that represents that. So you're going to have a primary equation, the equation that gives a formula to the quantity to be optimized, and a secondary equation that's going to provide information so that you can kind of complete that primary equation, and this will determine the domain constraints. I think you'll see this in action when we do an example. So let's go to our first one here, and this is probably a classic problem that you've seen something similar before, maybe even in algebra. But we're asked to find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. Okay, I think you've probably done stuff like this. So look, let's let x equal our first number, and we're going to let y equal our second number. Okay? And we want the sum, x plus 2y should equal 64, and the product should be a maximum. So x times y should be a maximum, right? Okay, well, the first thing I'm going to do is solve x plus 2y equals 64. I'm going to solve that for y and kind of isolate a variable. Now, you could solve it for x if you want. It really doesn't matter. But I'm going to have 2y equals 64 minus x, so y equals 64 minus x over 2. Okay, so now I know that f of x, are the equation that we're going to maximize here, is going to be equal to x times y, which in this case is equal to x times 64 minus x over 2. All right? So if I rewrite this, I get 64x minus x squared over 2, which is going to be equal to 32x minus 1/2 x squared. Now, in order to maximize this, we're going to take our derivative. So f prime of x is going to be equal to 32 minus x. We set that equal to 0. So x is going to be equal to 32. All right, there's one of our numbers. We found x. Well, now we need to find y. Well, y is just going to be 64 minus 32 divided by 2, which equals 32 over 2, which equals 16. So our two numbers are x equals 32 and y equals 16. Okay, that's it. We maximized it. Let's do another one with a little bit more real-world-ish applications in it. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Well, this is a great question, and one that I've seen apply to my regular life because I am from Iowa. I'm going to write that down. You should remember that I am from Iowa. Important information. Remember that. I'm from Iowa. That's the state I'm from. Okay, Mr. Winokur is also from there. So, the first thing that I'm going to do is I'm going to kind of draw a little picture. Just like with related rates, drawing a picture can be helpful to kind of clearing up what we're looking for. So we've got a river here, right? River, water, woo! And we're trying to draw a fence around a pasture that runs along this river, right? So we've got kind of our x value here, our y value here, our x value here. The pasture has to contain 180,000 square meters. So the area, which would be equal to x times y, has to be equal to 180,000. And our perimeter is, of course, going to be equal to 2x plus y, all right? Because that's all we're fencing. We don't need to fence in the river portion. The cows will just, I guess, wander in there. I don't know. So we have a formula for perimeter. We have a formula for area. Well, we can isolate one of these. So we can say that x is going to be equal to 180,000 divided by y. Okay? So now I'm going to substitute. So our perimeter is equal to 2 times 180,000 divided by y plus y. I already don't like how I did this, but I'm in it too deep now, so whatever. So it's equal to 360,000 over y plus y, which is going to equal, I guess if I multiplied this by y over y, I'd get 360,000 plus y squared, right? Hopefully that makes sense. Let me pause for a second and check my math here. Okay, I think I forgot a denominator. Woo. Over y. All right, and I'm kind of running out of room, so I'm going to go up here. So now I'm going to use this equation. So x is equal to, and this is a messy problem, but I believe that we can do it. Actually, before I even do that, I should find my derivative. So before I do that, my derivative, p prime of x, is equal to, and this is, I don't actually need this, so I'm going to erase it. Erase, erase. I don't need this right here. So p prime of x is equal to the negative 1, negative 360,000 over y squared plus 1. I think that's correct. So I set this equal to 0. So negative 360,000 is equal to negative 1. This is over y squared. So negative 360,000 is equal to negative y squared. So y is equal to plus or minus the square root of 360,000, which is equal to, I think it's going to be 600. Plus or minus 600. Well, we can't have a negative amount of fencing, right? So y is equal to 600 meters. So what's x equal to? Well, x is going to be equal to 180,000 divided by 600, which equals, I believe it should be 300. Good, I'm right. So x equals 600, or x equals 300 meters, sorry, 300 meters. And y equals 600 meters. Okay? Now, before I move on, I'm going to erase the fact that I'm from Iowa. Hopefully that gives you a hint of something, anything. All right, let's do another problem. We're going to do 3 more. Okay? So, an open box is being constructed from a piece of sheet metal, 18 inches by 30 inches, by cutting out squares of equal size from the corners and bending up the sides. What size squares should be cut to make a box of maximum volume? And what is that volume? Okay, so first I'm going to draw the box. All right, so we've got a box here. The box is 18 inches, so this is 18 by 30. This is 30. Okay, and it's going to cut out equal size squares. So in the corners, we're going to cut out equal size squares, right? And these squares are going to be sides of x. Okay, so x, 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 x. So the volume of this, well, what's the volume of this box going to be? That's what we're asked, right? So the volume of our box is going to be equal to this, which here is 18 minus 2x, 18 minus 2x, times 30 minus 2x, that's this length here, 30 minus 2x. So that's our, like our length and our width times our height is just x, okay? So now I'm going to multiply this through. Our volume is going to be equal to 4x cubed minus 96x squared plus 540x. Might want to check my math. All right, now we're going to optimize this. So what size squares should be cut? That's what we're trying to find, what our volume is and exactly what size squares we're cutting out. So we're going to find our derivative. So v prime of x is equal to 12x squared minus 192x plus 540. We're going to set that equal to 0. I can factor out a 12. So I get x squared minus 16x plus 45. Oh, this is Interesting. So I think I'm gonna have 9 and 5? That doesn't make sense, does it? One second, I gotta pause here. It won't factor, so we have to complete the square. Woohoo! 12 times x squared minus 16x plus 45. 16 divided by 2 is 8 plus 64 plus 64. Or, nope, not. This is equals 0. And actually, this should be minus, because I would have added it to both sides, right? So this should be a minus 64. So now we have, I'm just going to get rid of this, no, so 12 times x minus 8 squared minus 19 equals 0. Don't I still need that? One second here. I think I could have divided by 12 up here and just kind of gotten rid of it. And that should make things better. So x minus 8 squared equals 19. So x equals 8 plus or minus radical 19. Okay. But if I calculate that, if I have 8 plus radical 19, that's 12.35. And if I have 8 minus radical 19, that's 3.64. Well, because if I had two 12.35s, this would be 24. I couldn't take that out. It's too big. So x has to actually be equal to 8 minus radical 19, which is about 3.641. Okay? So that's the length of the square. The square is going to be 3.641 inches squared, right? And so our volume is going to be equal to 18 minus 2 times 3.641 times 30 minus 2 times 3.641 times 3.641. And I'll calculate that. 2 times 3.641 times 30 minus 10 equals, I think I did it wrong, but anyway, I believe the answer should be 886.553 inches cubed. Okay, good. Now, if there was anything that you were wondering about, it might help to notice here that the domain of x has to be between 0 and 9, right? Because it can't exceed 18 there. So that's something to take note of while you're doing these optimization problems. All right, 1 second. Okay, first of all, I wrote 555. It's not. It's 553. But anyway, I did do the math right. I typed it in wrong, but then I fixed it. Okay. Second to last one. I know it's getting kind of long, but I want to do as many examples of these as possible because I do think that they can get kind of tricky. And this is a great free response type question. So something to really know about how to do. What are the dimensions of an aluminum can that can hold 40 inches cubed of soda and that uses the least amount of aluminum? Assume the can is cylindrical and capped on both ends. Well, we need to know our surface area. What's the surface area of the can? Okay, first I'm going to draw our can here. Doesn't have to look great. Well, we got to have it, right? So this is our radius and this is our height. And our surface area is going to be equal to 2 pi r squared. Those are the end caps there. You see that, all right? Good. Plus 2 pi r h. That's this the outer cylinder part, right? So we want to be able to figure out here what's our radius. Well, the can holds 40 inches cubed of soda. So our volume is equal to 40 inches cubed. And the volume of a cylinder is equal to pi r squared h. So 40 is equal to pi r squared h. And we want to just kind of get this in terms of h or r, and I'm going to get this in terms of h. So h is going to be equal to 40 over pi pi r squared, right? H is equal to 40 over pi r squared. All right, so now that I have that information, I can rewrite my surface area, which is equal to 2 pi r squared plus 2 pi r times 40 over pi r squared. And I can cancel out a pi, can cancel out 1 r. So I get our surface area is equal to 2 pi r squared plus 80 over r. Okay, so now I can find the derivative of that, which is going to be equal to 4 pi r minus 80 over r squared. All right, set this equal to 0. So 4 pi r is equal to 80 over r squared. So I end up having 4 pi r cubed is equal to 80. R cubed is equal to 80 divided by 4 pi. So r is equal to the cubed root of 20 over pi. All right, beautiful. So our height is going to be equal to 40 over pi times 20 over pi to the 2/3 power, right? And I'm just gonna take these and calculate what they are kind of to a decimal place, because otherwise we're going to be dealing with a mess here. So this is about 1.853, and this is about 40 divided by, goodness, what a hot mess. 20 divided by pi to the 2/3. Okay, I got 3.707. So the can dimensions, R is approximately 1.853 inches, and our height is approximately 3.707 inches. All right, looks good? Okay, one more final example. I know this video is getting really long, but I just want to emphasize that lots of examples can be really helpful for really kind of learning how this works. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? Okay, we're going to have to pull in some distance formula here, right? So first thing I'm going to do is graph 4 minus x squared. 4 minus x squared, just to kind of see what that looks like. Okay, it's upside down. And I'm going to kind of graph this on my paper here. So if I trace, I've got 0, 4, and at 2, 0, negative 2, 0, it looks kind of like this, right? Okay, and we want to know what point is closest to 0, 2. That would be this point right here, right? So we're going to first use the distance formula, but we're going to use the distance formula from here to here. What is this point? Well, this point we're going to call x sub 1, y sub 1, okay? So the distance formula is, our distance is going to be equal to the square root of x minus, now remember that this point here is 0, 2. So x minus 0 squared plus y minus 2 squared. All right? Well, y is equal to what? We can actually substitute in for y. So our distance is equal to the square root of x minus 0 squared plus 4 minus x squared minus 2 squared. Does that make sense so far? All right, so I'm going to clean this up a little bit. So I get the square root of x squared plus, this is going to be 2 minus x squared squared, which becomes the square root of x squared plus 4 minus 4x squared plus 4x, nope, not 4x, x to the 4th. I just misspoke there. Plus x to the 4th. That's still all underneath the radicand. So that's equal to x to the 4th minus 3x squared plus 4. Just leave it like this for right now, okay? So now g of x, that's going to be what's under the radicand, because we can use the radicand for finding what's underneath the radicand, or the radical, what's underneath that, for finding the smallest critical value. So I'm going to call this value just g of x. So g of x is equal to, can you see all this okay? G of x is equal to x to the fourth minus 3x squared plus 4. So g prime of x, right? This is still going to be our smallest value if we're using this, is 4x cubed minus 6x, and I can set that equal to 0. So I take out a 2x. I'm left with 2x squared minus 3 is equal to 0. So x can be equal to 0, or x could be equal to plus or minus the square root of 3 halves. All right? I know, this is getting really, really complicated, right? But we can power through. So this was the first thing we did. This is the second thing we did. Now we're going to do our third thing. What are we going to do? We're actually going to do the first derivative test. All right, so I have 0. I have radical 3 over 2. I have negative radical 3 over 2. That should all be under a radical there. So if I test this, over here, this value is going to be positive. This value is going to be negative. This value is going to be negative. This value is going to be positive. So f of x, my fourth step, f of x is going to be equal to 4 minus plus or minus the square root of 3 halves squared, which means f of x is equal to 4 minus, or anyway, I'm not going to calculate all that. 4, it's going to be, f of x is going to be equal to 5 halves. Okay, so where is the graph closest to the point 0, 2? Well, we can't just use 0 because it is at 0, right? Right? So when x, this is our fifth step, when x is equal to plus or minus radical 3 halves, the points closest to 0, 2 on the curve y equals 4 minus x squared are, and we are actually just going to use these points, radical 3 halves, 5 halves, and negative radical 3 halves, 5 halves. Okay? That one was pretty complicated, I know, and really awkward, but I wanted to show you that example so you could see how it all works. Hopefully it makes sense, and I went slowly enough. Any questions, leave them in the comments, or just ask them in class. I'll see you there. Bye!